break time is over, and I hope everybody's back from break. So 426 in base 10 equals to what in base 8 using Ladix divide method? Huh? Is 652. Good. Now we're gonna use Ladix multiplied method, which is also used to convert fractions with this underlying theory. We have NF in base A, which is equals to B minus 1, B to the power minus 1, plus B minus 2 times B to the power minus 1, and so on and so forth, till B minus M to the power of B minus M. So we have this underlying theory to do a base conversion by using what we call lattice multiply method. So here is the procedure. We have f equals to this number, and f in base A. We have to compute the digits for bi in base I for I equals to 1 till m to the ni. So we have to multiply fi by b in base A, and we have to produce the integer I, which represents this number, and the fraction is this one. So converting each digit bi in base A to into the base B, we're gonna have a simple example with this multiply method to convert a fraction from one base to another. So we have this example. We have 0.4. We have 0.479 in base 10. I can hear people who are talking. If you are not talking, you can go out. I want you found this representation of this fraction in base 10 in base 8. How much is it? So what you're gonna do, you take this number, you take 0.479 times 8. Then you found what? How much is it? It is 3.832. Then you take the fraction, this fraction, 0.832, 0.832 times 8. Then you found how much? You found 6.656. Then you take 0.656 times 8. How much is it? Is 5.248. Then you take 0.248 times 8. Then you get 1.984. So you can keep continuing doing this, and you have to know that this is the least significant bit. This is the least significant bit, least significant digit, and the most significant digit is this, the first one. This is the most significant digit. So found the fraction representation of this number into base 8 is it is in base 8. We have to write 0 here. We have found 0, 0, and because we have these 3, which is the most significant digit, we have 3. It has to be like this. Then after 3 comes 6. Then after 6 comes 5. Then after 5 comes 1. So this is the representation of 0.479 in base 10, and this is representation in base 8 by using the multiply method. So this is the most significant digit, and this is the least significant digit. It's quite easy. What you need to do the multiplication. So we have the same fraction, 0.479 in base 10. We wanted to find its representation in base 2. We do the same. Hello? Is this method clear? We do the same. We have the fraction 0.497 times 2, we get this 1. Then we take this fraction times 2, we get this 1. Then we take 0.9160 times 2, because we are in the base 2. Then we found this 1, and so on and so forth. So always remember, this is the most significant digit, and this is the least significant digit. Thus, we have this binary representation of 0.479 in base 10, and its equivalent representation in base 2. This method is clear? Good. Now, we have algorithms for base conversion. For example, we have the first one, the second one. To convert a number n from base A to base B, we use the series substitution method with base B arithmetic or the lattice divide that we have got time to do some examples. Or we can use also the multiply. That is the last example that we just learned. And also we can use the second algorithm to convert a number n from base A to base B. We use also the series substitution method with base 10 arithmetic to convert a number n from a base A to base 10. And also we can use the lattice divide or the multiply method with decimal arithmetic to convert a number n from a base 10 to base B. So algorithm number 1 is short, but is a bit difficult. But the second one is longer, but is much easier and is less error prone. I would suggest you to use the second one. All right. Now we are going to learn about signed numbers. Signed numbers. Signed numbers representation. We have n. If you still remember, we have got the representation, positional representation of a number. We have also learned about polynomial representation of a number. Now we still have the same representation here, starting from n equals to a minus a n minus 1, a n minus 2. We have dot dot a 1, a 0. Then we start with a minus 1. There is a dot here, a minus 1 till a minus m, and here we have what we call base. Now, because we are now talking about sign magnetic method, we need to add here plus and negative to indicate that here we have positive or a negative number. So this can be get in between the parentheses to be S to represent this signed magnitude number, and we have a n minus 1, a n minus 2, dot, 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 till a1, a0. Then we start the fraction number, a minus 1 till a minus m, and we have the base sign magnitude number. Now we have s is equals to 0 when it is a positive number, and it is equals to r minus 1 for a negative number. If we have this r, if you still remember, is a radix, is a base, and this s equals to 0 when we have a positive number, or s equals to r minus 1 when we have a negative number. Clear? So if we are in base 2, to represent a negative number, we need a 1 before the number itself, because we have 2 minus 1, this is a 1, so that's why we have 1 in front of a negative number in binary. So we have this 15, we have n equals to 15, for example, in base 10. So this is 15. So 15 in binary, 15 in binary equals to 1, 1, 1, 1, right? Yes? Binary in 15. Now, we wanted to represent minus 15. Minus 15 in binary. So we have minus 15 in base 10 equals to what in base 9, in base 2? It is r minus 1, 1, 1, 1, 1 in base 2. Now, because we are in base 2, r equals to 2, right? So 2 minus 1 is 1. Clear? Hello? Clear? In base 10, if you want to represent this in base 10, we have 10 minus 1 is 9, so we have 9, 15. That is 10 signed magnitude. Signed magnitude. Clear? So you can add a comma here to differentiate the number itself and the signed magnitude number. Clear? Now, complementary numbers. We're gonna learn 1 is complement and 2 is complement. We have radix complement, r is complement, and it is given by this expression, n r equals r to the power of n minus n in the base r. So where n is the number of digits in this number, and the positive 4, we have this number, and the negative 1 is this number. So we're gonna have 1 is complement or 2 is complement. We have 2 is complement of this number. We have, for example, n equals 2 to the power of 6 minus this number, because 6 we have 1, 2, 3, 4, 5, 6. We have 6 digits in this number. That's why we have 2 to the power of 6. 2 to the power of 6 we have 1, and we have 6 digits after 1. So minus this number, so we get this binary representation as 2 is complement. So if we discard the carry, we have this number. plus its complement plus its complement, we get 0. Hence, we have the complement of the number n, which can be used to represent this number. So 2 is complement of this number is this one when we have n equals to 6. We have 1 we plus 6 zeros after 1, then minus the number, then we get the 2 is complement of this number. Same goes for 10 is complement. If you have this number, we have this number in decimal, so we want to find 10 is complement to this number. We have this number, since we have how many digits? 1, 2, 3, 4, 5. We have 1, then we add 5 zeros after 1, minus this number, and we get 10 is complement of this number. 10 is complement. So to find the NR, given the NR, found the complement of a number, given the number itself, you need to copy the digits of n. If you have 6 digits, you have to copy the digit of the number, beginning with the least significant digit, and we have to proceed toward the most significant digit until the first non-zeros digit has been reached. So, and we needed to replace a by r minus ar. We have some example. 10 is complement of this number. We have this number. 10 is complement. You have to take 0, 1, 1, 1, 1, 2, 3, 4, 5. You have to write 1, and you have to copy the digit of n, beginning with the least significant bit till you get the most significant bit. Then minus this number. Then you get 10 is complement of this number. 2 is complement also goes like the 10 is complement. You have this example, and 2 is complement of this number equals to this number, and we have n equals to 8. So we need to put 3 zeros in the most significant position and apply algorithm number 4. So the same rule applies to the case when n contains lattice points. Now we have algorithm number 5, which also have to replace each digit in the number representation and then add 1 to the result. You need to add 1 to the result. For binary numbers, r equals to 2, complement of each digit, and you have to complement each digit, and you need to add 1 to the result to find the 2 is complement. So found 2 is complement of this number. Algorithm number 5. Algorithm number 5. You need to find 2 is complement. And it is very important in computer system because it allows us to avoid subtraction. Instead of doing subtraction, we do addition, and this is gonna help a lot. So we have this number. We have n equals to 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1. This is the number that we have. Now, first replace each digit a of this by this number, and then add 1 to the result. What we do, you see, we needed to complement the bit. We needed to invert the bit. The first thing you do, you need to invert the bit. If I invert this bit, I will get 1. If I invert this bit, I will get 0. And if I invert this 1 is 0. Invert this 1 is 1. inverted this one is 1. If I inverted this bit is 0, and this one is 1, and this one is 1. So this is 1 is complement. We call it 1 is complement. And to get the 2 is complement, you need to add 1, but in which position? To the least significant bit, to the least significant digit. And the least significant digit is here. Then we get 1, 1, 0, 1, 1, 0, 0, 1. So this is 2 is complement. Clear? So if you have this number and you wanted to find 2 is complement of this binary representation, the first thing you do, you invert all the bit. So 0, if you invert the bit 0, it's going to be 1. If you invert the bit 1, it's going to be 0. If you invert this bit 1, it's going to be 0. If you invert this bit 1, 1, 0, 1, 0. This is 1 is complement. So after you found the 1 is complement, you needed to add the 1 to the least significant bit. The least significant bit is 0. Then you get this number, which is the 2 complement of this number. Clear? Hello? Clear? Clear? There is a mistake here. All right. Now I want you found 2 is complement of this number. Found 2 is complement of 64. Like we use this one. Found the 2 is complement of 64. 64. Use 8 bits, okay? Use 8-bit representation. Then found 64 is representation. 2 is complement. So the first thing you need to do, you need to convert the decimal to binary. Then found the 1 is complement. After found the 1 is complement, add the 1 to the least significant bit to found 2 is complement. Do it fast. Hello? Do it fast. Tell me how much it is. 64. 2 is complement of 64. Use 8-bit representation, okay? 8-bit representation. 8-bit representation. have done, tell me how much is it. So first, convert 64 in binary. Then found the 1 is complement. To found the 1 is complement, you need to invert the bit like I did here. Then you add the 1 to the list significant bit. Tell me how much. One. Okay, we're gonna do it together and found the right answer. Now, listen. I found that some people, they still have some problem to convert decimal number into binary. They are still doing division. This is gonna take you too much of time, right? I have seen people doing this. 64 divided by 2, then 32 divided by 2. This is gonna take you some time, okay? So listen and follow me. Now, if you know how many numbers representation you're gonna use is quite easy. Now, I told you please use 8-bit representation. Okay? You know that. Listen. You know that in 8-bit representation, the most significant bit is 128, right? So you are looking for 64, right? You do 64 in binary is how much? We have the most significant bit is 128. So we have 128, 0, right? Then we have 64. Yes, we have 64, 1. That's it. Then 32 is 0. 16 is 0. 8 is 0. 4 is 0. 2 is 0. 1 is 0. Clear? Then you have got 64 in binary. How many you have? 1, 2, 3, 4, 5, 6, 7, 8. So this is 64 in binary. Right? Yes or no? So we have 64 in binary. We wanted to find 1 is complement of this number. I need to invert the bit. If I invert this bit is 1. This is 1. If I invert this bit, this is 0. Right? Then how many left? We have 6 zeros left on this side. So we have 1, 1, 1, 1, 1, 1. How many? 1, 2, 3, 4, 5, 6. Then we have 1 is complement of this number. Okay? Then you add 1 to the least significant bit. You have 1 here. Clear? Now 1 plus 1 is 0. 1 plus 1, 0. 0. 0. 0. 0. 1, 2, 3, 4, 5, 6, then 1, 1. Clear? Hello? Clear? So some people, they still have some problem to represent a decimal number in binary. Don't use the addition method. The division method is gonna take you too much time. So if I do this, 62 divided by 2, I get 32. 32 divided by 2, 16. 16 divided by 2, 8. It's gonna take you more time. You know that this is the position. This is 128, 64. Because we have 64, we have 1 here. If I have 65, I should have replaced this 0 by 1. Okay? Now, make sure you do know how to represent a number in binary. Now, I want you found 46 is 2 is complement. Now, what you do, I have 128 64. Okay? 32. Okay? 46 minus 32 is 14. So I have 32. There is no 16. I have 8. So 14 minus 8. How much left? 6. Okay, good. I have 8. Do I have 4? Yes. 4. 6 minus 4 is 2. Do I have 2? Yes. 1. I don't have 0 more. Clear? Then you just got 46 representation in binary. Clear for everybody. So after you get this, you do inverted the bit. Once you inverted the bit, you add 1 to the least significant bit, then you get the 2 is complement of a number. Questions? Questions? Now, we have radix complement number system. I'm going to emphasize when you do have to calculate 2 is complement of a number. It is always for a negative number. The 2 is complement of a positive number is the same number. Now, we have positive number. This is much. And we have negative number. an minus 1, an minus 2. This is the representation of the negative number. We have 2 is complement of this negative number. 2 is complement number. Representation is this one. If you have n equals to this binary representation, for n equals to 8, you have this much number to get is 2 is complement. Now, radix complement number system, we have 2 is complement number system, representation of minus 18, n equals to 8. So we have plus 18, and we have minus 18. We need to calculate is 2 is complement. So decimal representation of n is this much. Now, we are going to consider these radix complement number system which are used to convert subtraction to addition. So I want you to pay attention to this. We use this radix complement number system to convert subtraction to addition. Subtraction to addition. Subtraction to addition. Why? To make it much easier for our computer to perform addition instead of subtraction. I'm gonna give you some examples. So we have these 3 cases. We have these 3 cases. We have A equals B plus C. A equals B plus C. And we have A equals B minus C. And we have A equals minus B minus B minus C. So we need to know why it is very important to have 2 is complement of a negative number. All right, now we have case 1. A equals A plus C. That is fine because we have only positive number. For example, we have 7 in base 10 plus 4 in base 10. We need to find how much it is using only 5-bit representation. We have 7, we have 4, and always remember 2 is complement of a positive number is always the same number. You see, we have 7 is This is the representation of 7 in binary. And we have 4 representation of 4 in binary using 4 bits. Then we have to add a 0 in the front in the most significant bit to indicate that this is a positive number. So we need to do the addition of these two binary representations, 7 plus 4. So there is no overflow. Hello? There is no overflow. You have 0, 0, 1, 1, 1, which is 7. Then we have 0 and we have 1, 0, 0, 0. This is 4. If you do the addition of these two binary, you have bit per bit. You have 1 plus 0, you have 1 plus 0, you have 1 plus 0, and you have 0 plus 1, and you have this much. There is no overflow. There is no overflow. All right, so this is the representation of this number. No, there is a mistake here. There is a mistake here. This is not 4. This is 8. This is 8. This is 4 here. You should have found it. We have 4 plus 7. So this is 1. This is 1. This is 0. And this is 1. So 4 plus 7, we got 11, and there is no overflow. Now we do the same for 9 in base 10 plus 8 in base 10. Then we get the binary representation. If you do binary representation of 8, 8 we have 1, 1, 0, 0, 0. And for 9 we have 1, 1, 0, 0, 1. This is 9, 1, 0, 0, 9. And since we have both negative number, we need to add a 0 in front. So there is 0 plus 1, this is 1, 0 plus 0, 0, 0 plus 0, 0, 1 plus 1, we have 0, and here we have 1. This is what we call overflow. Overflow. All right. Now, case number 2, we have one negative number is we have A equals B minus C, and we have to calculate the 2 is complement of minus 9. For example, here we have the example. Here we have 14 in the base 10 minus 9. This is a simple example of this. We have to perform addition instead of subtraction. Now, we need 2 is complement of a number to calculate, to make, to convert subtraction to addition. This is gonna make the work much easier to the computer system. Now, take away for this. 2 is complement of a positive number is the same number. Okay, we don't need 2 is complement of a positive number. We need only 2 is complement of a negative number to convert subtraction to addition. Clear? We don't need a 2 is complement of a positive number. We need a 2 is complement of a negative number. For example, we have 14 minus 9. 14 minus 9. Hello? Tell me 14. We have to use how many bits? 4 bits or 5? We have to use 1, 2, 3, 4. We have to use 4 bits. 14. So if you have 14 minus 10, how much is it? Now, we need 14 in binary. How much is 14? 1, 1, 0. 1, 1, 1, 0. Now, because it's a positive number, we don't need to calculate 2 is complement of this positive number. We only put a 0 to indicate that this is a positive number. So we have 2 is complement of this number. Now we have minus 9. Minus 9 in minus 9, okay? This is minus 9. Minus 9 is 1, 0, 0, 1 in binary. Now, because this is a negative number, we need to find 2 is complement of 9. So how much is it? 2 is complement of this number. How much? Hello? How much is it? Huh? 0, 0, 1. This is 0, 1, 1, 1. Very good. But because it's a negative number, we needed to add a 1 in front. We needed to add a 1 in front. 2 is complement. Now, instead of doing subtraction, we do addition. So we have to do this number, 0, 1, 1, 1, 0. This is 14 in 2 is complement plus this number, 1, 0, 1, 1, 1. 2 is complement. Then we found what? We found this number. What is the current? Okay. How many minutes? 2 minutes? Okay. Okay, to show me that you understand that, I'm gonna give you a simple exercise to do. Use 2 is complement, okay? I'm gonna give you a simple one. 64 how much is it? Use 2 is complement. Use 2 is complement of minus 32. How much is it? Use 8-bit representation. You only need to calculate 2 is complement of 32, okay? You don't need for 64 because it is a positive number. Quaila, only 2 minutes. If you finish, you go. If you don't finish, you stay here. No lunch, okay? Try to be fast. Finish it, okay? You finish it? No, use binary. Use binary representation. Binary representation. 2 is complement. Binary representation. Okay, that's it for today's class. We're gonna continue next week. Enjoy your weekend, but remember, I have uploaded homework number 1. Please try to do it before the deadline. See you next week.